Just preparing to stream. I want to start letting people in. I was surprised, like we had like 150 registrations for like this last meeting, and I thought there would be less because it's just right before Christmas.
Yeah.
people have nowhere to go, so
Exactly. I think that's the thing.
yeah.
Everybody's working from home, so it's really the same.
Because I think initially when we were,
also just want to get a reminder and see it later when it's on YouTube or something.
Right. Yeah, I remember like when we were deciding, we were like trying to figure out whether we even wanted one on the 23rd because of the, you know, how close it was to Christmas.
Yeah.
I was surprised by the number of registrations. Okay, so it's already streaming.
Okay, I'm going to try and go into the studio and see what I can see.
I want to admit everyone.
Yes, it says it's live. Mm-hmm.
Yep, it's live. Okay. Now there's going to be like a feedback loop with the live version now, with me playing the live version.
You can just close the.
I did. Now I did, yeah.
Okay. It happened to me last time. Thank you so much, Sophia, once again for agreeing to be our guest this evening. Or,
sure.
Or today, wherever you happen to be now.
It's almost 6 p.m. in Portugal.
Okay.
So it's fine. It's a reasonable hour, I think.
Wonderful. It's 7 p.m. I'm in Germany, so not too far away from you.
Yeah.
Yeah, I'm gonna probably turn off the waiting room as well, because people are gonna keep joining. All right. So maybe we should start. Hello, everyone. I'm TC, and welcome to the last Earth Engine virtual meetup for the year. And today we are going to have like two parts. We are going to have first a presentation, and then we are going to have a more of a Q&A for the presentation, followed by if you have any questions about Earth Engine, you can ask us, and we will try to answer them. So starting off, we can one second. Let me see if I have. Let's start by thanking Sophia for agreeing to present today. She's a postdoctoral researcher at the Portuguese Institute for Sea and Atmosphere, it's at IPMA. And she recently worked on a paper on creating a land surface temperature estimation module for Earth Engine using the Landsat series. And she's going to be talking to us about it today. If you have any questions, you can use Slido. Basically, all of the questions will be added to a list, and we can go through them at the end. Here's the link to Slido on the chat. and you can use the event code EEVM to ask your questions. So with that, Sophia, please tell us what you worked on.
Hi, everyone, and thank you for inviting me for this meeting, and thank you all that are attending. And I hope I can explain a bit about, or explain what this work is, and maybe answer some questions you might have. As TC just said, we have this paper published recently where we provided Earth Engine code to derive LST from the Landsat series. So I have a PhD in geophysical sciences with applications to remote sensing, and my PhD was pretty much on land surface temperature retrieval from satellites. And that's what I've been working on since then within the Landsat, which is part of the EUMETSAT. So it's the European Agency for Meteorological Satellites. So I have a large experience with land surface temperature estimation. And I want to start, wait, not moving. Okay. So I want to start this presentation by explaining why we did this work. So we are a European agency, so we really don't have to process satellites that are not European, but I had this student doing a master thesis on the urban Italian effect in Coimbra, which is a Portuguese city in the center of the country, more or less, close to the ocean. And as you know, to study the urban island effects, it's desirable to use a satellite that has high spatial resolution. And so we decided to use the Landsat. Now, she was, her master degree was on geology, and she didn't have much experience programming. They don't have many courses with programming at her course at her university, so I thought it would be interesting for her to use the Google Earth Engine. And then there weren't that many Landsat LST datasets over Portugal available, so what I proposed was that we would work on deriving our own LST for Landsat, and then she could use it to do her study on the urban island effect. And as I said, because she didn't have much experience programming, I thought it would be easier for her to learn how to use the Google Earth Engine instead of learning Python and then having to process all the data, which can be quite complicated. And the GE simplifies a lot of the processing. So even though she had to learn a bit of programming, I did a lot of parts of the module, so she had to learn a bit to use it and everything, but thought it would be easier. So she helped me with the algorithm development and calibration, and then we set up everything to run on the Google Earth Engine. And the good thing was that from there, she didn't really need to have many resources to work on her project. And she could do the full analysis of these large volumes of data directly in the Earth Engine, wherever she was with her laptop. And she was pretty much very independent in working with the data. So I think this is a benefit of using the Earth Engine, especially for students that don't have usually access to a lot of resources to process the data. And so we started setting up a production chain for what we call a production chain for the Landsat land surface temperature. The algorithm we decided to use was the statistical mono window algorithm. So this algorithm only requires one infrared channel, which is what is available on the Landsats. And this was developed by the ClimateSat for the older generation of satellites that also only had one channel. And this is a very simple algorithm. It's simple linear regression that depends on the brightness temperature of the infrared channel, and then requires an estimate of surface emissivity. And the tricky part of using the algorithm, the thing that, so this is very easy to apply, but the thing that usually users don't easily have access to is the algorithm coefficients. And to have a robust calibration database that represents all possible situations when the satellite is retrieving LST, that is the tricky part. And this is something I work with her, and we use the radiative transfer model to simulate several atmospheric and surface conditions and what the satellite would measure, and then calibrated the algorithm with this data. And for this algorithm in particular, what we do is we separate or we break apart situations depending on the content of water vapor in the atmosphere, which is the main atmospheric component that interferes with the signal in the infrared. And to account for their interference, what we do is, instead of having explicit dependence, we just break apart situations where you have different water vapor contents and calibrate the coefficients for each sort of bin of water vapor in the atmosphere. And this is the calibration residuals for each Landsat. And as you can see, the algorithm works reasonably well. Obviously, as you go towards the very high water vapor contents, you start to have larger areas because of the interference of the water vapor in the signal. But this is just something that we really can't do much about, especially when you only have one channel. So when you have two channels, you can work with the difference between the two channels to try to improve or try to solve this problem in the signal, or this limitation of the signal. But when you have only one channel, it's natural to have higher errors as you go towards higher concentrations of water vapor. So if you want to access the code and look at it as I'm going through it, these are the links. So there's the up one is directly for the Google Earth Engine repository, and afterwards, after the paper, I also created a GitHub repository. So because there were some people having trouble accessing the Google Earth Engine one for some reason, so I just decided to create a GitHub one. That's the reason why it's not. So this link is not in the paper, but if you want to use it, you can also use it. The code is up to date with the one in the Earth Engine. And I'd like to start by saying this because I've had so many people asking me, contacting me, asking me this. So when you click the link, this is what will show up in your window. And the script area will be blank because this is a link to a repository, not a script. So this script section will be blank, but the repository will show up in your scripts tab. So although it looks like the link is not working, so I had a lot of people contacting me asking why the link was not working, if I could provide a new one. The link is working, it just, the code will show up in your scripts tab. So I just decided to add this here because it seems like it's a thing that happens to a lot of people. And I don't know, maybe somebody with the same question might see this video, and this is where the code will be. So now going through the structure of the code. So there are several phases of data processing before you can compute the land surface temperature. And there is a main script, which you could call a wrapper. So this is something you usually use in computer science. And it basically loads all the modules and defines all the links, the paths to the data, everything that is necessary for the code to run. So it will load all the image collection that it's necessary based on the user selection. So if the user will tell the code, which Landsat and what is the date range they want to process and where do they want to process. And the code, this code will load all the data and call all the necessary modules to compute the land surface temperature, and then returns that data set. So now I'm going to go through the rest of the code. So the first phase is to characterize the surface, because we need to know what is the surface conditions to estimate or to have a better estimate of the emissivity. And to do that, we use the NDVI. So this is the normalized vegetation index. I'm not sure if all of you are familiar with this. So this is simply an index that is used to establish how green vegetation is. And in this case, because emissivity is very sensitive to contrasts between the vegetation and non-vegetated areas. So vegetation usually has very high emissivity values, and bare soil can have much, much lower values. So typically, to estimate emissivity, we just use a weighted average between what's green and what it's not green, and take the emissivities of those two components, and we can get a pretty good estimate of the emissivity at a pixel scale based on the subscale information that we have on the vegetation fraction. And to do that, we will need to load the surface reflectance data. So to compute the NDVI, somebody has their mic on. So to compute the NDVI, you need to have surface reflectance data. You cannot use the top of the atmosphere values because it will have, atmospheric interference. So first step obviously is to mask any clouds, because we cannot get any signal under the clouds. And then the NDVI is a very simple computation. It's just the normalized difference between the near infrared and the red channels. And then we convert those NDVI values into a fraction of vegetation. And why we do that is because, so the NDVI is very useful, but it will be for when you have very low values of vegetation, it will quite be sensitive to what's is on the soil, what type of soil, what type of surface, if it's water, if it's not. And in this case, we don't really want that information. We just want to know how much vegetation is in the pixels. So we set up a minimum NDVI value for which we assume anything below that value will simply be bare. So there's bare in terms of vegetation. So there is no vegetation below a certain value, which we take from the literature to be 0.2. And on the other extreme, NDVI values tend to saturate as you go towards very high values of vegetation. So what we do is we set up a value of NDVI from which any value above, it's just very dense vegetation anyway. So, and that value we also take from the literature to be 0.86. So basically we go from having NDVI having a value between 0 and 1, which will be an indication of the fraction of vegetation inside the pixel. So the next phase of the code is to then, since we already know how much vegetation we have for that a given observation, is to compute the emissivity for that observation. And to do that, so as I said, the emissivity of vegetation is quite stable. It's very high and usually quite stable. So it doesn't vary much with vegetation type. There are slight variations, but it's much lower than the variations we see for bare ground surfaces. And to get a good estimate of those bare ground emissivities, it's the tricky part. So what we do is we use this database from Aster that uses the direct retrieval of emissivity. So the algorithm that is used separates the emissivity temperature signals and gives you a direct estimate of the emissivity of the surface. The problem is, and it's also a very high resolution data set, the problem is that the aster has very low a very low number of overpasses over a given period of time. So to get a full global coverage, what the authors of this data set did was they average all the observations for several years. So what you have is sort of a climatology of emissivity over the globe. And they also provide the respective climatology of NDVI. So your emissivity is a static emissivity. And in places where you have a lot of vegetation variability, like a seasonal cycle, or even from one year to the other, you can have significant changes in emissivity. The emissivity might not be well represented. So that's where our fraction of vegetation that we just computed goes in. So how do I combine these two data sets? So as you remember, I said before that we compute emissivity simply assuming that there's vegetation and there's something that it's not vegetation. We call it bare ground. And the emissivity of the pixel will be a sum, and weighted average, let's just say it, of the vegetated component and the bare ground component. And the weight is simply the fraction of vegetation. So the vegetated part, as I said, is pretty stable, takes very high values, so we can just assume typical value from the literature. And then the bare part is what we'll be getting from the aster. And to do that, we simply invert this equation. So we have the emissivity estimate. We can compute the fraction of vegetation from the aster NDVI that is provided, and taking a value of vegetated emissivity of 0.99, we invert and can get the bare ground emissivity. Now, afterwards, this bare ground emissivity will be used in another module, combined with the fraction of vegetation that we computed from the Landsat. So it's the actual vegetated fraction of vegetation of that at that time. And we just apply the same equation, also using emissivity for vegetation of 0.99. So here, there are several values. If you work with this type of data, there's a lot of values showing up in the literature. I did extensive research on this and found that it seems that because this is very high resolution data, the best estimate or the best value to use would be a very, very high value. So 0.99, some other papers use 0.98. But it actually seems from our quality assessment that using 0.99 works better. But if you find that it's not taking, or you don't have good enough values over the area you're studying, this is something you can always change in the code, obviously. One of the benefits of having the code fully available on the Google Earth Engine, is that you can change anything that you need for your application. So this is just to show you the importance of doing all this NDVI correction, I would say. So this is the aster fraction of vegetation we computed from the NDVI and the respective band 14 emissivity, which is the band that it's closer to the Landsat infrared band. And you can see here the difference. So this is a climatology, and then the Landsat image I'm showing here is around May, which is springtime here in Portugal, and you're starting to have a lot of very, very green vegetation around this time. So you can see the difference between having the two data sets here. You have much greener areas, sort of, and that translate into much higher emissivity values when you compute the emissivity. So this will have a large impact on the LST estimation. Finally, the last phase of the, almost, I would say, close, I don't know how you say it. So it's not really the last, but almost at the end now. So an important step as well, because as I said, the algorithm takes into account the water vapor content of the atmosphere. So we need to get that information. And the way we do that, we get the water vapor estimates from the reanalysis, from the NOAA reanalysis. And because, so this data is 6 hourly, so the way we do to get the actual or a better estimate of the water vapor at the time of observation of the Landsat, because in 6 hours you can have significant variations of water vapor. Usually they are not very large, but in some cases when you have fast moving systems and things like this, you can have significant changes in water vapor within 6 hours. So what we do is we take, so this code, it seems very complicated, but it's basically here we just select the dates we want to use to filter, to set up our date range to load the reanalysis data. And then for each one of those estimates, which are every 6 hours, this will be 2 full days, we compute the time distance to the Landsat observation time. And then we select the 2 closest ones, which in the end will be simply the one right before and right after the Landsat observation time. And then this is simply so we select those 2, take the water vapor, take the time difference, and do sort of an average. So this is simply a linear interpolation between the time before and the time after to get the best estimate of water vapor at the observation time of the Landsat. Then, because the algorithm does not require the water vapor explicitly, what we need is to convert that into the beams that I used to calibrate the coefficients. So we use beams with steps of 6 centimeters for the water vapor. So this is just the way we convert the water vapor values into beams. And then we just add that information to the image collection. So now the final part, the final module, we compute the LST. So we have the water vapor beams already available, and we use that to map the coefficients into the image. I'm not showing here there's a module with all the coefficients available. I'm not showing here because it's a lot of code and there's not really much information, but if you want to see it, you can access the repository and just check it. And what we do, we map the coefficients, and then we just apply the algorithm I just showed you. So A, B, and C, and there's the emissivity we computed and the brightness temperature from the satellite. And this is the example that's in the paper. You have here the brightness temperature of Landsat and the respective land surface temperature. You can see high differences between the two due to the atmospheric effect on the data. So I wanted to sort of wrap up this talk by showing you just the quality assessment we did. So we were careful to evaluate how good our LST estimates were, and to do that we compared with several in situ stations that are typically used to validate land surface temperature for several products available, modalities, etc. So these are all the stations that we used. Results are pretty good, so we're very confident on the quality of the product. And then if you want, or if you have a station or you want to check the code that we used to extract the time series that were then compared with the in situ data or the station data is fully available on the repository. It's the example 2 code. And you can see here, it makes this nice time series of the whole Landsat series. And on the bottom of the script, there's a little bit of code that is commented that you can use to extract the data if you need. And there's also another example file in the repository that shows you how you can use the code to generate, to process, or to compute the LST for one given image, and then plot it in the map together with a bunch of other variables available. Then there's also some code available that shows you how you can extract the images, which is what I used to make all those images that I showed you before and the ones that are in the paper. I processed them with another software afterwards, so they could have all the scales and the color bars and everything. Unfortunately, to my knowledge, Earth Engine, or at least when I did this paper, the Earth Engine didn't allow us to make pretty pictures, let's say it like this. As you know, when you're publishing a paper, you need to be careful. You need to put all the geographical referencing in the image and the color bars, and it's not easy to do this in Earth Engine for now. So I hope this will change soon. So what I did, I extracted a GeoTIFF and then uploaded it to a different software to get the images. But I think with the examples, you can easily see how you can use the code for your applications in case you need it. And that ends my talk. Thank you all again for attending. And if you have any questions, I hope I can help.
Thank you, Sophia, for that presentation. I think it's really interesting, and I'm sure a lot of people are going to find this code useful. And I already told you that I'm already using it.
Yeah, I've had several users contact me saying they are using the code, asking what they can do to change different questions, which is really, really nice. I think I work with data production for quite some time now, and you don't have as much contact with users. It's interesting to see when they find your work very useful for their applications. And I've even had some users suggesting changes to the code. So I've made few simple changes to the code thanks to these users. Thank you so much. So this is a good thing as well for having, one of the good things of having the code available. Even some minor bugs sometimes slip. So it's really, really nice.
So let's thank Sophia, and let's see if anyone has any questions. If I can share the screen, I can then pull up the Slido link. Sophia, can you maybe stop sharing? Then I can share. Okay. So this is if you go to the Slido page, which I already linked, you can use the EEVM event code to get to the Slido page, and you can ask questions, and then we can probably take a few questions because we do have some time left. You can also use the QR code to go to the Slido page if you want. See the chat. Okay, that's just. Okay, let's take a few questions. So the first question is, Sophia, what do you think are potential areas of improvement for the algorithm?
So there were some, in terms of the actual code, there were already some suggestions to make it faster, and I implemented it and it really helped. And I think there are still some sections, so I'm not a programmer. Whatever I did here on Google Earth Engine, I learned it from my from Googling it basically. So I'm sure there's still area of improvement there, but it seems to work quite all right. The code, when there's a large amount of data, it takes a bit more time to run. But I
Yeah, I've
think
run it
there.
globally and it works. I mean,
So yeah,
I have to
that's
map.
good.
I have to map over it. Like I have to map over it. I think separate countries or something. I remember. I don't remember exactly what I did, but it does work. It takes some time, but it works.
So maybe another area that still needs a bit of work, but I think that's general for the LST products. It's the emissivity. So there's still a lot of uncertainty related to the emissivity. Unfortunately, it's a very tricky problem because it's very high correlated with the LST. So it's really hard to separate the signal from the two. And I think there is still a lot of work to be done here. As I showed you, I was sort of trying to mix data sets to get the best emissivity estimate possible, but even the Aster data set, I think there are a few problems related to the algorithm itself because it's a difficult problem. So I'm hoping that maybe in the future we can get some other data sets which we could
Yeah, I recently, I
use.
think I read a paper or watched something where they talked about the huge emissivity issues in particularly sub-Saharan Africa. Like they don't have a
Mm.
lot of these actual ground-based emissivity measurements. So you you're left with like enough differences that the LST, like you use like Stefan Boltzmann, you get a large difference in actual temperature from the same radiance. And you said you started with the urban, you started with like urban heat island was like one of the projects, which is why you got into this. So same for urban areas, right? We don't really have much in terms of emissivity estimates for urban areas as a whole.
That's the thing. It's the I think the worst part is that it's very difficult to measure in situ. So uh, even when we measure at a small scale, we still don't know exactly how that translates into a large scale. We are doing this sort of averaging between components. We are assuming that it works, but it should not be exactly that physically. So I'm sure there's still a lot of
Mhm.
work that can be done in that sense.
So another question is, do you have any plans of doing something similar with the two thermal bands of Landsat 8?
That
It's
is
a
a good
split window
question.
one, I think.
No, because one of the bands is not working
Oh,
correctly. So initially, so this work for my master student, she only wanted to work with Landsat 8. So we were first calibrating and trying to apply a split window algorithm. And then I started to read some papers about this problem in the calibration of one of the channels. And it's there's problems there. I don't think they have fixed that yet. And we even tested the algorithm, and the LSTs were really bad. So we compared with the station. So we decided to go with a single channel algorithm, and that was in the end useful because it meant that we could just process all the Landsats with the same algorithm. But until they fix the problem with the channel, I don't think we can move into a different algorithm.
right. Uh, so could you please explain the cloud mask you have used?
So the cloud information comes with the data set. So if you use your search bar and put in the data set, Landsat data set, and it shows, then there's a window that shows up showing, I guess you can show, yeah. So if you type Landsat 8 or something, yeah, just open one. So in the bands, you will see there is a
The quality control.
The quality control band, and there you will have here, bit, in this case, bit 4, I think. So there's information on so I'm using the USGS cloud masking basically. So it comes with a product. I'm just applying it. I'm not computing it myself.
Could you explain how the algorithm coefficients? Okay, let's talk about that later. So did your validation consider differences in overpass time related to orbital drift?
I would say yes. So we always take the actual observation time that is available in the file, and then the station measurements are performed every minute, so we can have an actual, so the match in time with the station is pretty accurate. It's down to the minute. So the orbital drift it's something that it's quite common in the polar orbiters, and it's as long as you have the actual observation time, which is available in the files, you can do this very easily.
So the last question, and maybe you will have to share your screen for this, is could you explain how the algorithm coefficients work in a bit more detail? I can stop sharing if you wanted to show the equation or something.
I'm not sure I understand the question, but
I'm assuming it has something to do with that equation for the mono window algorithm.
Yeah, I'm gonna share it here. So I need to share my screen. Oh, you have to let me share. I can't share for some reason.
Wait, you cannot share?
Yes. It says that you have deactivated the sharing.
Okay, I'm gonna make you a co-host and let me know if you can share now.
Oh yeah. So can you see my slides? Yeah.
Yes.
So how it works is that we kind of force the relationship between brightness temperature. Instead of using Planck's function, we force it to be a linear equation, sort of. That's the way the algorithm works. And to get, it will not, should not be perfectly linear, but it will be close enough for our purposes. And the way we do it is to get these coefficients, we create an artificial database. So we have a lot of profile data from the atmosphere, temperature profiles, atmospheric water vapor profile, ozone profiles, and then we set up a surface as we like. What I usually do, I like to set up several ranges of land surface temperature based on the 2 meter temperature, and different ranges of emissivity as well, so we can account for different conditions in real life, let's say. And then we just put everything in a radiative transfer model, and the model will simulate for those surface conditions and that atmosphere what will be the brightness temperature that will be observed by a satellite. And when you have a lot of profiles and a lot of surface conditions, you can put everything together in the radiative transfer model, and you sort of create an artificial database of the relationship between that, where you can get the relationship between LSTs and brightness temperatures. And then to get that relationship, there are several algorithms available. This one is pretty simple, so we decided to use this one. And to account or to try to optimize the algorithm, because as you go towards very high water vapor content, the signal starts to be weaker and weaker. So there's a lot of absorption of the infrared radiation by the water vapor. To account for that effect, what we do is break apart the data into beams of water vapor content and calibrate the model or the algorithm for those beams of water vapor. So we will have different coefficients for each water vapor condition. And I guess I can show you here. If you go to the code and here the coefficients, what you will see is that for each one of those beams of water vapor, you will have a set of coefficients. And then there's also a set of coefficients different for each Landsat because the bands are not exactly the same. So you need to account for that. And then when you're computing the LST, you just have to select the appropriate coefficients to get the best estimate, I would say. I'm not sure if that is the question, if that helps or not.
I think that was, yeah, that helped more. Like I didn't know about all that, so that was very interesting to know.
Okay.
So I think there was one more question about like nighttime data because that's also important. But
Yeah, so from the point of view of the algorithm, I think it can easily be adapted to run with nighttime data. So we would just have to use the NDVI from the previously available daytime observation, because the problem with the nighttime is you don't have the visible channels that are used to compute the NDVI. But I remember searching, and I don't think even the infrared data for nighttime is available, is it?
so I think
Or not
there
on
are a
Google Earth
few.
Engine?
They're not on Google Earth Engine. I think there are like a
Yeah,
few select nighttime values, but I don't think if it's even in the actual archive uh,
yeah. I don't think
discussion.
it's still available, but I think if they make it available, we could easily adapt the algorithm to compute those values. I don't think that would be a problem.
Okay. So thank you, Sophia. I think that was all the questions we had. I'm gonna move on to the next part, though I don't know how many. Yeah, we have like 15 minutes left now. But let me share my screen. Um, so now it's time for like some troubleshooting tips and tricks. If you have any questions about using Earth Engine, if you have run into an issue, you can ask us, and we can try to answer. Can give you a few minutes if anyone is interested in asking any questions. Sophie, I had one question, I guess, about the use of the atmospheric water vapor content, I guess, from, I think you said NCEP, you used NCEP NCAR
Yeah.
reanalysis. Would you expect significant differences with different reanalysis products?
Yes. I mean, the difference is not, I mean, it's the impact on the actual land surface temperature values is reduced because it's really how you select the coefficients. There are very few situations where you have very fast moving systems or fast convection and then raining. So these situations where you can have small or high variations in a short time period where you can really jump from one bin, like very high water vapor, to very low suddenly, that could be where you can get higher errors in your LST. And one way we know that having higher temporal resolution can help solve those systems a bit better, but still there are still some uncertainties associated to the modeling of those systems anyway in any reanalysis. So I don't think it would be interesting to see if we get very high differences, but I don't think it's the main. I think, well, with land surface temperature, the main uncertainty source, it is the emissivity, unfortunately. So unless you're going to very, very moist areas where you have very moist atmospheres and a lot of fast moving systems or convection, it should be, but in those situations, usually there's also a lot of clouds. So then you have the problem of cloud contamination in the data. So I guess,
so
I don't think it would be.
I mean, I think my question came more from like I have worked with a lot of these more like current generation reanalysis, ERA 5, NSAP Encounter Mera 2, and I think also NOAA series DOE and the Japanese reanalysis JRA 55, I think. And I have not looked at water vapor content. I've looked at cloud cover, and like the average cloud cover can go like almost 60% higher.
But cloud modeling, it's much more difficult than water vapor. Because it depends not only on the water vapor content, but on other stuff. So although you can have large differences in cloud cover, it might not translate in very high differences in water vapor. So, but this is something I've never really looked at.
It would be interesting to look at, I think.
Yeah, of course.
So I don't think we have any questions for us. So this is the last meeting, as I mentioned, of the Earth Engine virtual meetup. And in January, there are no meetings. And the first meeting of next year is on the 10th of February, which will be hosted by Sabrina Zito. And it will be on a harvested forest regeneration from space using Earth Engine for Canada's landscape by Jennifer Hurd at the University of Calgary. And if anyone has any questions, I probably will wait around for like 10 more minutes. Otherwise, thank you. And if you want to be a speaker in 2021, please contact Sabrina Zito. And thank you for well, it was not a great year, but thank you for a very successful Earth Engine virtual meetup. Sabrina, do you want to add anything?
Well, first I want to say as well, thank you, TC, for being a wonderful co-host for this season. It's been great collaborating on these twice a month meetups. And thank you also so much, Sophia, for your wonderful talk and presentation. You really demonstrated your teaching skills with the great explanations of the concepts behind the code.
I hope it was clear.
Yes, and how the code works. So thank you so much again for the time you took to prepare this presentation for us. And yeah, so we look forward to Jennifer Hurd's presentation in February, and we encourage everyone to stay in touch via Twitter, and please feel free to leave your Twitter handles in the chat so we can follow each other. Yeah, so that's all from my end. Back to you, TC.
All right, thanks, Sabrina. Yeah, I guess again, I'm gonna probably stay around for 10 more minutes if anyone has any questions. Sophia, maybe we could talk about like the emissivity thing. I would love to work on that more because I've been doing it with the code now, like changing the emissivity and checking how that affects the urban heat island. And I think the different reanalysis might also be interesting. I know Earth Engine now has the ERA 5 reanalysis, but it does not have the column like
it doesn't
water
have
vapor.
Yeah, I went out. Well, obviously, I mean, the reason I don't want to sound that I'm not giving credit to the NSAP reanalysis is pretty good. The only reason I used this one, I didn't really have a choice because it was the only one available on Google Earth Engine that would go far back until the so that all Landsats were covered, and it was global as well. So this was the only one available. Preferably, I would have used EVA 5 as well, but water vapor is not. Total water vapor is not available yet.
So have you taken a look at the USGS provisional land surface temperature data for the US?
I have not, because this was really focused on Portugal, the study, and there was no data available. I think now there's a new version available that it's global, right? I haven't looked at it.
I don't know if they released it. I remember like even the US one was supposed to be. I don't know if it's on Earth Engine.
I
I don't
think they
think it
have
is.
it planned, at least planned to be
Okay.
released soon. I
But
think.
for the US, I think they were using the NAR reanalysis, which is I guess slightly higher resolution. I don't know how much difference you would expect, but uh, I guess like something to think about like at some point in the future. I would love to.
So my experience with not using different, so in where I work, we usually use the European Center predictions or the reanalysis data. So that's what I'm used to work with. But my experience with doing all the traceability of the uncertainties is that um, the uncertainties related to the water vapor, in the case of these algorithms, it's usually quite low.
Okay.
So I would expect it to have be important if you were using an algorithm like the TESS, which is the one used for Aster, and there's also some MODIS and VIIRS data. That one is much, because it does the full radiative transfer with the radiative transfer model, that one is much more sensitive to the atmospheric data. But not just because it doesn't use just the water vapor, it's the full profiles that it needs to run. So that one is quite sensitive to the atmospheric correction. This type of more statistical algorithms are quite robust in terms of the atmospheric component, because you have to really change a lot the water vapor content to have very different coefficients. So usually the uncertainties are really, really low. Mm-hmm. But then they are very, very sensitive to uncertainties in emissivity, which we have quite large. So if that's something you can work on, it's very welcome.
Right. Yeah. Hopefully like I will get some time to work on it next year. Like probably once I'm done with my PhD.
Yeah, I have plans to do some work on that as well, but it keeps getting.
We should collaborate.
Yeah, it keeps getting.
Yeah, delayed.
Yeah, because I have other things to do, but yeah, that's something I really want to. Especially for the next generation of, we will have now the next generation of European geological satellites, and we really want to prepare and try to improve our algorithms for that, those new sensors. So
right,
that's something I want to work on as well, but it's a difficult problem.
Yeah, it's just there's always a paper to revise. It's just getting. All right. Thank you again, Sophia. And maybe we can. I guess most people have started leaving now. So thank you again, everyone, for joining throughout the year. And see you again next year. And have a great, I guess, happy holidays, and have a great new year ahead. Bye.
Okay. Bye, everyone.
Thanks,